Hi everyone. In this video, we're going to go back to some of the ideas about rate of change that we discussed in the very first section of this unit. So you hopefully remember, and if you don't, you can flip back in your notes or go back to the old video. We had two definitions. We had the average rate of change. That was just the slope between 2 points on any function. And we also had the instantaneous rate of change. That was the slope of a function at 1 point, or at least as the 2 points get squeezed infinitesimally small, infinitely close together. That was the one where we had the limit statement to figure out the slope, and we had something like this. So basically we had our two y values, h distance apart in the x direction, and then we squeezed that distance between them to 0. We have a couple more definitions for you today. Secant line might be one that you worked with a little in geometry. It's a line that passes through any 2 points on another graph. So like if we had a quadratic here, just some basic quadratic, and here's point A, here's point B, the secant line would be the line that passes between those 2 points. Here's the main idea here. The slope of the secant line is the average rate of change between those 2 points on the original function. And then we're going to have one other tangent line, which you've talked about tangents in geometry, I think. We talked about the tangent function in pre-calc, but this is going to be just a little bit different. Or is it? We'll talk more about that later. A tangent line is one where the slope is equal to the instantaneous slope of the function. And I don't want to say it just passes through 1 point, because obviously if you have like some repeating function, then a tangent line could possibly intersect it twice. But the point is, wherever you build the tangent line, it's only intersecting the function once. And the most important thing is that the slope of this tangent line matches the slope of the function that it's being put on at a single point instead of across 2 points like we talked about with the secant line. So our first couple examples here are reviewing these rates of change, and then we're going to bring in these new types of lines. So in example 1, we are tasked with finding the average rate of change of the function. Then we're going to use that to write a secant line. Okay, well, average rate of change, that's just the slope. Between 2 points. So let's see, here's our interval. So let's do second point minus first point over x value minus x value. So, okay, that would then be the cosine pi over 2 minus cosine of 0 over pi over 2 minus 0. Thinking about my unit circle, the cosine of pi over 2 is 0. The cosine of 0 is 1. And then pi over 2 minus 0 would just be pi over 2. And if we just clean this up so it wasn't a nested fraction, we'd end up saying the average rate of change would just be negative 2 over pi. Then we're tasked with building a secant line. And as always, you need two things to build a line. You need a point and a slope. Well, we have our slope, and we need a point. Well, we have 2 points. We figured them out. It doesn't matter which you use. Just like all the way back in Algebra 1 when you were using point-slope form. In fact, that's what we'll use to build the tangent line and the secant line here. We're just going to rearrange it a little bit. This is probably not the way you're used to remembering point-slope form. Your algebra teacher probably had you remember it this way. I guess we're just going to simplify it once, where we're going to take the y value and add it over the other side. That way it's at least isolated for the dependent variable. So let's plug in what we have. We have our slope, negative 2 over pi. We're going to leave x, subtract, how about pi over 2? We could use that point. And then our y value at that point was 0. So you could say plus 0, or adding 0 doesn't do anything. So you could leave it like this. Or your other acceptable answer would be using the other point. So y equals same slope And the other point was at x equals 0, but it had a y value of 1, which this would be fine. Hey, nice thing about AP, they don't care if you don't simplify some algebra things. This is one of them. So like, don't bother distributing the slope here. We have more important calculus things to do than to, do some 8th grade algebra. If you want to visualize this before we move on, real quick, we know that the cosine function starts at 0 and it's going down, and it crosses, it has its x-intercept at pi over 2. And conveniently, whoops, these were the 2 points. Okay, why are you doing that? Stop, please. Those were the 2 points that we used in this problem. And then the secant line would look just like this. Cool. Let's turn the page. Okay, so just to remind you, I've reprinted the instantaneous rate of change formula up here. You'll see an A in there. A is just any x value where you actually want the instantaneous slope. So if you want the instantaneous slope at 2, you're going to use A equals 2. Later on, we'll also use a form of this where we just leave x in there. So you can just remember it like this if you would like as well. Doesn't matter to me. And then we need to talk about one vocabulary term. If you've taken physics, you should have heard of this by now. But just if you haven't taken physics or you've forgotten, here we go. The word normal in a mathematics sense does not mean ordinary. Sorry. What it does mean is perpendicular. And you might say, okay, well, why would you say normal when you could just say perpendicular? Well, technically, normal is more specific than perpendicular. If you stick with calculus for a long time and you start talking about 3D graphs, normal means perpendicular to a plane instead of perpendicular to a line. So like, think about the desk that you're working at right now. The normal, well, no, I don't want to confuse you. Just know normal is like perpendicular for now. If you get to calculus 3, normal is going to be more specific than perpendicular. There you go. And hopefully that turns our frown upside down. Okay. Example, find the slope of a curve at x equals 6. Okay. And it just gives us 1 point, so that means we have to be working with the instantaneous rate of change. That would be the slope at a single point, which would be that limit stuff up here. How about let's use 6 as our value in here for a, or x if you were like remembering this one. So f of 6 plus h minus f of 6. And then let's go ahead and substitute this stuff into the function. So 2 over 6 plus h minus 3 minus 2 over 6 minus 3, all divided by h. Okay, this could get fun. Let's see. We can at least reduce this second one here. You should be really nervous when I give you a whole page for a problem, by the way. Well, maybe not really nervous, but no, it's going to take a while. Okay, can we clean up the first one? Well, we can at least do the 6 and the minus 3, so how about 2 over 3 plus h? And then for the second one, we'd have 2 over 3, which is about as much as we can do, and we're going to divide that all by h. Well, can't really do anything with this h until we've put together these two fractions up top. So I think we're going to need a common denominator here. Yep, okay, so let's multiply each of these by the other one's denominator. So let's see, that would give us 6 over, and maybe we don't distribute the denominator for now just because we're lazy. We might have to eventually, but sometimes you don't, and I'm a lazy guy. I mean, efficient guy. I'm an efficient guy. I don't want to if I don't have to. Okay, so now we have a common denominator, so we can actually work this subtraction. Hey, be really careful with this. When people are subtracting this kind of fraction, I see this mistake all the time, and it drives me nuts. They write it like this. Do you see the mistake here? It was minus the whole fraction, which basically means minus the whole numerator. So I always stick a set of parentheses around there to remind myself, oh yeah, I have to actually distribute that. So that'd be 6 minus 2h over 3 plus h. And then we still have that pesky divided by h at the bottom. Well, okay, 6 minus 6, that's 0. And then, hopefully we're almost done here, right? I'm running out of room. So we have negative 2h. Still have that denominator that we didn't multiply out. And then how about instead of dividing by h, let's say times 1 over h, because, haha, we can get it to divide out here. Whoops, parentheses, 3 times 3 plus h. And we're finally at a place where we can actually substitute in 0 for h and have something come out. We get negative 2 over 3 times 3 plus 0 equals negative 2 over 9. There's our instantaneous slope of that curve at the point x equals 6. Okay, before we finish, we are tasked with finding the tangent line and the normal line at that point. So let's start with the tangent line. As you know, I like to abbreviate things, so we'll just say tan line. You don't have to actually write out the point slope form every time, but I will, at least for the first few lines, so y'all can follow my work. We've got the slope already, but we need a point. So let's come back to the function real quick. It's y equals 2 over x minus 3. Let's substitute in 6 real quick. Oh, I guess we already had that somewhere up there. Oh well. 6 minus 3 equals 2/3. There it was. That's the point we were looking for. Sorry. Oh well. We have slope, we have a point, so we can figure it out. There's our slope. Our x value was 6, and our y value was 2/3. Again, don't waste your time simplifying. I am more interested at this point in you being able to do calculus than you being able to do arithmetic. Then I'm out of room, so I'm going to do the normal line here. Remember, normal, just fancy word for perpendicular at this point. The only thing that's going to change is our slope. Perpendicular slope, opposite reciprocal, just like your 8th grade or 9th grade teacher told you. So 9/2. But hey, the point is the same, so we don't have to change the other stuff. Boom. All right, if you turn the page, you'll notice our next example is also an instantaneous rate of change problem. So this is one I could have given you back in section 1. It says, how fast is the rocket climbing after 8 seconds? It's not saying how fast was it climbing during the first 8 seconds. It's saying how fast is it climbing at 8 seconds. So that tells us we're going to be looking for the instantaneous rate of change, or slope. So that's going to be your limit function again. And what I'd like for you to do is to try this problem. Pause the video, try the problem, see if we end up in the same place. And in a second here, you're going to see all my work. So here it is. There you go. Hopefully you got 32 feet per second. Again, if there's context in the problem, I want you to answer in context. So here we had feet and seconds. So it is important that you label your answer in feet per seconds. When we get to the AP exam, and I know it's a long way away, but when we get there, sometimes if they don't really have a good calculus place to put the last point on a free response question, they'll give you a point just for labeling the units correctly. And when there's only 108 points on the AP exam, would you really want to give away one of those for free because you didn't write down the units? I know I wouldn't. All right, let's turn the page. All right, so this style of task is a little bit different. This time we're asked where, at what point. So where is the tangent line horizontal? Basically, where is the slope? 0. And I've got a definition over here just to lay that out for you. Tangent line or tangent is horizontal when it has 0 slope. And then remember from your algebra classes, vertical is when the slope is undefined. So basically some kind of division by 0. This one's a little bit different because it's not, hey, what is the slope at this x value? What is the slope at that x value? It's at what x value is the slope this? So we're going to have to use the more general version of the instantaneous slope formula here. Basically, you have to use x instead of a. And again, the reason why is because we don't have some number for x. We want to know where does this, so remember what I just wrote down, this is our slope, where is that equal to 0? And then we're going to solve that for x. Strap in, fasten your seatbelt. This one's a little bit different. Since we don't have the number, when we're evaluating this, you're literally just going to have to plug in x plus h into all the x's in the function. So we've got 2 minus 6. Now, normally it'd be 6x, but in our first one, it's x plus h. And then plus, normally it'd be x squared, but instead we're plugging in x plus h squared minus f of x. Well, that's our original function. Like I said earlier, be careful, make sure you subtract the whole original function. And we're going to divide all that by h. So this is going to be a ton of algebra, but basically this is going to give us a formula for the slope at any x value. Okay, so let's put on our algebra caps and get going. 2 minus, let's distribute that 6. 6x minus 6h plus and then we're going to subtract off all those things. Divided by h. At this point, everything without an h should subtract out if you did your algebra correctly. So like here's a positive 2, here's a negative 2. That subtracts to 0. Minus 6x plus 6x subtracts to 0. Plus x squared minus 6, or minus x squared subtracts to 0. At this point, we have limit as h approaches 0, negative 6h plus 2xh plus h squared all over h. Now we can divide out that denominator. That's negative 6 plus 2x plus h. And now we can actually plug in 0 for h, so that equals negative 6 plus 2x. Nice. So again, this is a formula that gives us the slope at any point. This is huge. This is an idea that we're going to work a lot with in the next chapter. For now, let's just address the 2 questions. Or I guess it was just one question here. The question was, where is the original function slope equal to 0? So I'm just going to put in 0 for the slope, which now it's a quick algebra problem. Add over the 6x, divide by 2. At x equals 3, the slope is 0. Let's just find the y value for that. What was the original function? Oh, yeah, it was all that stuff. 2 minus 6x plus x squared. I think negative 7, I think, for the y value. So again, that means at this point, at 3 comma negative 7, f of x has a horizontal tangent. Hopefully that makes sense because this is a quadratic, right? It was positive x squared. Yeah, it was positive x squared. So it's got to open up somewhere. Wouldn't there be a horizontal tangent at the vertex? Cool. Nice work, everyone. See you tomorrow.